You know that shiny chrome logo on a car? Ever stop and wonder how in the world they get metal to stick so perfectly to plastic? It seems so simple, but it's actually a massive scientific challenge. So today, we're going to pull back the curtain and look at the incredible science that makes it possible to chrome the, well, unchromable.
I mean, seriously, think about it for a second. That little emblem has to put up with everything. Scorching hot sun, freezing cold winters, high-pressure car washes. So why doesn't that super thin layer of metal just flake off the plastic? The answer, it turns out, is this brilliant mix of chemistry and physics that completely changes the very nature of the plastic itself.
Okay, so to get why the solution is so clever, we first have to really understand the problem. And the problem isn't the chrome, it's the plastic. On a molecular level, plastics are just fundamentally slippery.
There's a scientific term for this. It's called low surface energy. And a perfect way to picture it is a brand new waterproof jacket. You know how water just beads up and rolls right off? That's because it can't wet the surface. Plastic is exactly like that. Its surface is so stable and low energy that there's just nothing for other molecules to grab onto. They literally can't form a strong bond. And this right here, this lays out the fundamental conflict. Plastic has low energy, it's tough to wet, and it's chemically inert. It just doesn't want to react with anything. And metal? Well, it's the complete opposite on every single point. So you're trying to bond two materials with totally opposite personalities. This is one of those cases where opposites definitely do not attract.
And as if that wasn't a big enough hurdle, modern manufacturing, specifically 3D printing, just tosses another wrench into the whole thing. I mean, 3D printing is an amazing technology, but it makes this adhesion problem way, way harder. That layer-by-layer process creates this microscopically bumpy and uneven surface, which is a total nightmare if you're trying to apply a perfectly smooth, uniform layer of chrome.
So if you can't get the chrome to stick to the plastic surface, what do? Well, you change the surface itself. And this is where the real genius comes in.
This is the big idea, the core innovation right here. Researchers figured out they didn't need a better glue. What they needed was to perform a kind of molecular surgery on the plastic, giving it a brand new metal-friendly skin that could finally form that strong, permanent bond they were looking for. And it happens in this really cool three-step transformation. First, they just zap the plastic with plasma. This does two things. It roughens up the surface on a nanoscale and creates these little chemical hooks. Then, using UV light, they graft a special molecule onto those hooks, creating what you can think of as a chemical handshake layer. And finally, a primer goes on top to act as the perfect bridge between this new skin and the metal coating. All right, so the surface is prepped, it's ready to go. Now it's time to actually apply the chrome. And here, too, modern science has a much better, safer, and way more precise way of doing things. See, the old way, electroplating, meant dipping parts into these huge vats of hazardous chemicals, including hexavalent chromium, which is a known carcinogen. It was messy, it was dangerous, and honestly, it often resulted in uneven coatings. The modern way is called Physical Vapor Deposition, or PVD. Inside a high-tech vacuum chamber, they basically vaporize solid chrome and then deposit it atom by atom right onto the part. It's incredibly clean, super precise, and so much better for the environment. And that's the magic combination. When you take the precision of PVD and use it on that newly modified plastic surface, you get a perfectly uniform, super dense metal film. You get to skip all the hazardous chemicals, you get rid of all the cracking and weird buildup from the old methods, and it's the absolute perfect solution for coating those complex shapes that come right out of a 3D printer. So this all sounds great in the lab, right? But how does it actually hold up in the real world? Well, the results are pretty amazing.
Get a load of this, 700 HV. That's Vickers hardness, which is just a way to measure scratch resistance. And to put that number in perspective for you, it's significantly harder than most stainless steel. So this isn't just some shiny, delicate layer. It's an incredibly tough, durable coating that can go toe-to-toe with coatings applied directly to metal.
This quote from the research paper really says it all. Cohesive failure within the polymer substrate. So, what does that actually mean? It means the bond between that new skin and the chrome is so ridiculously strong that if you try to pull it off, the plastic itself will break first. The chrome layer will not peel. The bond is literally stronger than the material it's sitting on. And this isn't just some science experiment. This is the technology behind the premium finish on your car's grille, the lightweight and durable parts in aerospace, that metallic shine on high-end electronics, and even the tough, sterile coatings on medical devices. It's what lets us have things that are both lightweight like plastic and durable like metal.
So the next time you see that shiny chrome logo on a car, you'll know the incredible surface science that keeps it from ever peeling off. It really makes you wonder, doesn't it? Now that we've solved the puzzle of the unchromable, what's the next impossible material that we're going to learn to master? Thanks for joining me for this explainer.